On the evening of the 6th of May, 2026, a highly organized and exceptionally violent convective storm system swept across southern and central Mississippi. Driven by perfectly structured supercells, this intense outbreak spawned at least 14 confirmed tornadoes, many of which carved remarkably long paths and reached significant intensities. The storms completely destroyed or severely damaged hundreds of homes and left 17 people injured. Fortunately, and quite miraculously, given the circumstances, no fatalities were recorded. To fully grasp the magnitude of this event, it is necessary to look far beyond the surface damage and deeply analyze how these storms formed, tracked, and caused such specific devastation. A thorough examination relies on official data from the National Weather Service, the Storm Prediction Center, advanced dual polarization radar, and on-the-ground reports to dissect the anatomy of this outbreak. Unlike typical summer thunderstorms that flare up and dissipate in less than an hour, supercells are the absolute apex of convective weather. They are the most organized, persistent, and dangerous storms in the atmosphere, capable of sustaining themselves for hours while traversing hundreds of miles. The beating heart of a supercell is the mesocyclone, a deep, powerfully rotating updraft, ranging from 2 to 6 kilometers in diameter and extending tens of kilometers into the sky. This rotation is not spontaneous. It is birthed from extreme wind shear, which is the change in wind speed and direction with height. Shear creates invisible horizontal tubes of spinning air in the lower atmosphere. When a powerful updraft catches one of these tubes, it tilts it vertically, establishing the storm's rotating core. During the Mississippi outbreak, the 0 to 6 kilometer wind shear reached an extreme 50 to 60 knots, while low-level helicity, a measure of the atmosphere's rotational potential, surpassed 150 square meters per square second. Simultaneously, a roaring low-level jet stream pushing 40 to 50 knots acted as a conveyor belt, pumping deep, rich moisture directly from the Gulf of Mexico. When combined with moderate to strong convective available potential energy, or CAPE, the significant tornado parameters spiked to between 2 and 4 across multiple areas. From a forecasting perspective, this signaled a critically high risk for strong, long-track tornadoes. From a purely dynamic standpoint, the mesocyclone meticulously organizes the storm's energy, allowing it to survive its own heavy precipitation. The rear flank downdraft acts as a crucial trigger. It wraps cold, dense air around the back of the updraft, physically tightening the rotation, much like a figure skater pulling in their arms, which frequently forces the tornado down to the ground. On modern radar displays, this physical process was glaringly obvious and terrifyingly pristine. Textbook hook echoes appeared. Velocity couplets tightened to extreme values, and crucially, dual polarization technology detected sharp drops in the correlation coefficient. This confirmed lofted tornado debris signatures, meaning the radar was no longer just seeing raindrops. It was tracking the shredded remnants of trees and homes being hurled thousands of feet into the air. These massive storms initiated along a slow-moving cold front, pushing from East Texas and Louisiana into Mississippi. By midday on May 6th, the Storm Prediction Center had already issued a level 3 out of 5 enhanced risk, explicitly highlighting the potent threat for multiple tornadoes. The first major supercell erupted near Adams County around 4:00 p.m., moving northeast at a blistering forward speed of 45 to 52 miles per hour. As it rapidly intensified over Franklin County near Meadville and Boone, the ultimate step was taken with the issuance of a tornado emergency. This is the highest and most dire warning possible, driven by absolute radar confirmation of a violent tornado bearing down on populated areas. The storm reached its absolute peak intensity as it crossed into Lincoln County, heavily striking the Bogue-Chitto area. Meanwhile, a parallel supercell tracked aggressively across Lamar County near Purvis, carving a continuous damage path nearly 16 miles long. Because these storms peaked during the evening, a deadly meteorological shift occurred. The loss of daytime heating caused the lower atmosphere to cool, reducing surface friction. Paradoxically, this actually increased the low-level wind shear. The resulting tornadoes were entirely rain-wrapped and shrouded in absolute darkness. Even the most experienced field observers and storm chasers could not visually identify them. Given their rapid forward speed and visual cloaking, last-minute evasion by the public was physically impossible. The resulting damage footprint was dictated not just by the raw, unyielding power of the wind, but by severe ground-level structural vulnerability. Nearly 500 homes and apartments were severely damaged or destroyed, including roughly 325 structures in Lamar County and nearly 200 inches Lincoln County. Herein lies a painful reality of extreme weather events. They starkly highlight socioeconomic disparities. Many of the hardest hit areas had high concentrations of mobile and manufactured homes. Even when properly tied down, these structures are simply incapable of withstanding EF2 to EF3 winds of 120 to 200 miles per hour. They were completely flattened, their frames twisted beyond recognition. Meanwhile, nearby site-built homes with proper foundations generally sustained only roof or window damage. Furthermore, the dense pine forests of Mississippi turned splintered trees into high-speed shrapnel, bombarding everything in their path. Because the storm struck at night, most people were indoors and relied entirely on emergency texts, weather radios, and warning sirens. However, the ability to rapidly reach a safe underground shelter varied greatly, especially in rural and lower-income communities, pushing initial recovery and infrastructure repair costs to an estimated $15 to $30 million. Tens of thousands lost power, major roadways were blocked by debris for days, and schools were forced to close. Despite this horrific destruction, the fact that there were 0 fatalities is nothing short of a modern meteorological triumph. When comparing this to the catastrophic 2011 super outbreak, which produced over 360 tornadoes and claimed over 300 lives, the 2026 event was quantitatively smaller. However, the critical difference was the timing. The 2011 storms struck largely during the afternoon, when people could see the threat and were awake. The 2026 storms hit after dark, a time statistically proven to double the fatality rate of tornadoes. The entire burden of safety shifted away from visual confirmation and fell squarely on automated warning systems and individual family preparedness. The survival of everyone in the storm's path stands as a sign of profound scientific and societal progress. Still, the 17 injuries, primarily from flying debris and collapsing walls, remain a heavy physical and financial burden for the affected families. The psychological trauma, the deep emotional toll of seeing an entire neighborhood permanently erased in a matter of minutes, will linger for years. Yet the rapid community response provided immense hope. Neighbors pulled neighbors from the rubble, volunteer groups mobilized overnight to deliver relief, and local officials coordinated seamlessly with federal agencies. This human element is just as critical as the atmospheric science. It reinforces a fundamental truth: while humanity cannot control the atmosphere, society maintains total control over its preparation, building codes, and community resilience. Placing this specific event into a broader climate context reveals a stark, undeniable trend that demands attention. The lower Mississippi Valley has experienced a highly active and violent spring in 2026, perfectly aligning with a decades-long data trend showing an increase in days with high tornado potential in the southeast. While the overall national tornado count may not be sharply rising, the spatial distribution is shifting, and the environment is becoming heavily loaded for concentrated violent outbreaks in what is now often referred to as Dixie Alley. A chronically warmer Gulf of Mexico provides an endlessly deep reservoir of moisture, while shifting jet stream dynamics create stronger, more volatile shear profiles. These climate factors do not magically spawn a storm out of thin air, but they load the dice. They ensure that when the ingredients do come together, the ceiling for violence is much higher. The Mississippi outbreak wasn't the largest in recorded history, but it perfectly and terrifyingly illustrates how rapidly atmospheric conditions can escalate. Looking ahead to the remainder of the season, the severe weather focus will predictably shift north and west toward the Great Plains. States like Oklahoma, Kansas, and Nebraska face the highest immediate risk, potentially seeing high-risk days if deep upper-level troughs remain stubbornly active. In the southeast, the threat profile will transition. There will be fewer isolated supercells and more quasi-linear convective systems, or QLCS. These massive squall lines produce widespread, devastating straight-line winds and brief, fast-moving, rain-wrapped tornadoes that form and dissipate in minutes, making them incredibly difficult to issue individual warnings for. Overall, the 2026 season is projected to finish near the statistical average, around 1,000 to 1,200 tornadoes nationwide. But the character of the season leans heavily toward high-shear, low-cape environments, the exact setups that favor fast, hidden nighttime twisters. Further extending this forecast requires a closer look at the macroscopic climate drivers currently at play. The atmospheric circulation in the late spring and summer of 2026 is being heavily influenced by a rapid transition toward La Niña conditions in the equatorial Pacific. Historically, this phase shift tends to alter the jet stream pattern, often pushing the primary storm track further north as the summer progresses. This allows an expansive, oppressive heat dome to build over the southern United States. Consequently, while the traditional tornado threat will peak in the Great Plains through late May and June, the mid to late summer months will likely introduce a pronounced risk for intense, long-track derechos across Midwest and the Corn Belt. These massive windstorms thrive on the northern periphery of intense heat ridges, riding the exact boundary where extreme instability meets strong mid-level atmospheric flow. Communities in the upper Midwest must prepare for hurricane-force inland winds that can flatten crops and devastate regional power grids in a matter of hours. Additionally, as the calendar inches closer to peak hurricane season, the historically warm waters of the Gulf of Mexico pose a compounding dual threat. Not only do they provide the continuous thermodynamic fuel for land-based severe weather outbreaks during the spring, but they also drastically increase the probability of rapid intensification for tropical cyclones later in the year. Should a tropical system make landfall along the Gulf Coast or the eastern seaboard, the resulting frictional shear created as the storm interacts with the landmass will almost certainly trigger highly concentrated rain-wrapped tornado clusters within the system's right front quadrant. This dynamic mirrors the precise rotational hazards seen in the Mississippi outbreak, but embedded within a much wider, prolonged disaster scenario. To meet these escalating and complex challenges, forecasting methodologies are undergoing a rapid evolution. The integration of advanced machine learning algorithms into numeric weather prediction models is actively revolutionizing the way marginal or complex atmospheric setups are analyzed. These models can now recognize non-linear pattern signatures that traditional physics-based models might underestimate, allowing meteorologists to issue earlier and more accurate outlooks for these highly conditional threats. These forecasts will inevitably evolve as new data streams into meteorological models, but the underlying urgent necessity remains constant. There must be continued investment in weather research, aggressively elevated building codes for mobile home parks, mandated community storm shelters, and the construction of an infrastructure grid that does not collapse at the first sign severe wind. Perhaps the most striking takeaway from the May 6 event is the glaring, unacceptable gap between scientific advancement and social reality. Advanced warning systems, dual polarization radar, and rapid smartphone communications have dramatically reduced fatalities to zero in this case. Yet the concentrated catastrophic destruction of mobile homes exposes a massive vulnerability that science alone cannot fix. As society looks to the future, the atmosphere will continue to demand absolute respect. It operates strictly on precise physical and thermodynamic processes, completely devoid of empathy. Complacency is the greatest societal risk. Years without a major disaster can easily create a false sense of security, but the atmosphere does not abide by human calendars. It will produce violent storms when the ingredients align, regardless of whether populations are ready or not. The 6th of May 2026 Mississippi supercell outbreak serves as a stark, uncompromising reminder of what is constantly at stake. The meteorological science is solid, forecasting technology is more powerful than ever, and warning dissemination is nearly instantaneous. The only remaining variable in the equation of survival is human action. To stay deeply informed with actionable expert-level weather and climate analysis, be sure to join American Sky Brief. Subscribe to the channel, turn on notifications, like and comprehensively share this video. American Sky Brief is dedicated to delivering timely, clear, and highly practical meteorological content so audiences can stay several steps ahead and better prepare for any weather scenario. Together, atmospheric knowledge can be turned into an impenetrable shield of safety for families and communities everywhere.